So in this problem, we're going to ask, does the series n equals 1 to infinity of the absolute value of sine of n factorial over n squared plus 1 converge or diverge? Now, if you think about this in the terms that most people learn to think about math, where they look at an expression and try to figure out how to evaluate it, you're going to get stuck here. Nobody knows what the sine of n factorial is, or what that looks like, or what it's, what properties it has. The important point here is that the sine of anything is bounded, and this is one of the reasons that we kind of kept hitting the squeeze theorem or the sandwich theorem in Calc 1, because that was the first place that you encountered an inequality, in particular a bound on sine, in order to make an argument. So like this. So the thing to observe here is that 0 is less than or equal to the absolute value of sine n factorial is less than or equal to 1. By the way, I just want to change the color there so it stands out. So this inequality is true, and therefore we can also say that 0 is less than or equal to the absolute value of sine n factorial over n squared plus 1, since that's going to be a positive denominator, which is less than or equal to 1 over n squared plus 1. In other words, all I did is I just divided all of these terms in the first inequality by n squared plus 1. You can think of the one on the left as 0 over n squared plus 1. I just divided everything by n squared plus 1 and got an inequality that was still true. So here I have my an, and here I have my bn. Well, actually, that's not bn yet. So this is certainly true, and we need one more step. We need to know that that's less than or equal to 1 over n squared. How do we know that? Because we're making the denominator bigger. So let me just take that away. I'm going to write the inequality that I actually care about. What this shows is that 0 is less than or equal to the sine of n factorial over n squared plus 1, which is less than or equal to 1 over n squared. In other words, if this expression here is less than 1 over n squared plus 1, and 1 over n squared plus 1 is less than 1 over n squared, then it's certainly the case that this term is less than 1 over n squared. So now I have, in terms of the DCT, that's my an and that's my bn. What I can now argue is that the sum of bn converges. Why? Because since bn is just 1 over n, that means that it's a p series with p equals 2, which is greater than 1. So it converges, and we can say therefore the sum of an, which is the given series. Note that here I've defined an to be that sequence. The series that I was given in the problem is the sum of an, and we can say that that converges as well. There we go. So so let's see. So this just demonstrates the point that sometimes you can't do a clean evaluation of the terms in the series, but you do have to use properties such as the fact that sine is always between 1 and -1. So in this case, the absolute value of sine of anything is in between 0 and 1. Oh, and also I just wanted to make one other point. When you write these statements, you should always be clear whether you're talking about the sequence or the series. If you're talking about the series, you should put the sigma in front of the term an or bn. It would be an error, for example, to say that bn converges because of p series, because bn is not a p series. Bn is just a sequence. So you do want to make sure to state it the way that I've said it here, that sum of bn with a sigma in front of it. Okay.